right, so I wanted to just do a simple example of a problem that we might run into in chapter 13. So chapter 13, the basis of it is to find what we call the equations of motion, which are the equations that tell us how an object is going to move. But they're all based in Newton's second law, where we're looking at the forces acting on the object. And from that, we can infer the acceleration, which we can then manipulate, as we did much in chapter 12, to figure out expressions for velocity and position, for instance. So here we have a problem where we have an ore cart. It has a mass of 400 kilograms. It's actually being pulled up the incline by a motor. So it looks kind of like a pulley, but it's supposed to be a motor. And we want to know, given the fact that the initial velocity is 2 meters per second, if the force that's being applied by the cable because of the motor depends on time in this manner, can we find the velocity and position of the object when we are at 2 seconds? So we're going to use the forces in the x direction. Of course, we're going to have our x-axis parallel to the incline, and our y-axis is going to be perpendicular to that. The forces we have acting on the cart are the force due to the cable. And then, of course, we have the weight. Keep in mind that if this is theta, this angle is theta as well. So because there's no friction reported in this problem, we only really need to look at forces in the x direction because we don't need to find the normal force for friction. So the forces I have acting are the force of the cable, so I'm just going to write that as F right now, minus mgx is equal to m times ax. So this is 3,200 t squared minus mg sine of theta equals m. And now I'm just going to call it a because it's the only acceleration we have in this situation. We weren't given the angle, we were given the ratios of the sides. So using that, I just want to take a note that the opposite side would be 8 and the hypotenuse is 17. So the sine of theta is 8 over 17 equals mass times acceleration, which is m times dv dt. So I'm going to divide by the mass, so I have an expression for dv dt. The mass, of course, is 400. So for the second term, because it just had the mass in, I just divided by the mass and got rid of it. And over here we have just dv dt. So I want to simplify this just a little bit by putting in the values that I know. And so now what we have is a differential equation of the simplest kind where we can just solve this and integrate after we separate our variables. So I multiplied both sides by dt because I want the time on this side and then just dv over here. Remember that my limits of integration have to match up, so I'm going to go from time equals 0 to some arbitrary time t. The velocity at that time equals 0 we're calling v naught, which actually we have a value for, that's 2. And then we're going to just have arbitrary velocity at time t. So this is going to turn out to be 8t cubed over 3 minus 4.61t equals v minus v naught, which is v minus 2 because we were told that v naught was equal to 2. And so if I rewrite it, I get v is equal to 8/3 t cubed plus, sorry, it was minus, I wasn't sure, minus 4.61 t plus 2. And keep in mind that this is ds dt, which we're going to use for our next step, where we are going to integrate again to figure out an expression for s as a function of t. However, we can use this expression and let t equals 2 to find out what that velocity is. And so through evaluation at t equals 2, I find the velocity is 14.1 meters per second. So I found my first thing that I wanted to find, which was that velocity. I'm going to take my expression for velocity and express it as ds dt. And then I'm going to integrate that again so I can get an expression for position as a function of time. Okay, so now I'm going to integrate over position. We start at the initial position, s naught, that corresponds to the position when t is 0, and then we integrate to some arbitrary time t, and that's when the position is. For this particular question, problem, we weren't really told that it had any special initial position, and because we could always start our origin wherever we want, we're just going to assume that our initial position is 0. So if I integrate the left-hand side, I get s minus s naught, but that's just 0 anyway. But I wrote it just for argument's sake. When I integrate the right-hand side, I get 8t to the 4th over 4, but there's also that 3 there, minus 4.61 t squared over 2 plus 2t. So s is equal to 2/3 t to the 4th minus, I never found out, 4.61 over 2 times t squared plus 2t. And so I can evaluate that at t equals 2 seconds. And that's my last thing that I need to do. And when I calculate that, I find that the position is 5.45 meters. And so that's the example. So it might not seem like we're doing anything different, but it's sort of the approach that's different, and it's that we're finding these expressions for acceleration now, given that we can identify what the forces are that cause them, and we relate the two through Newton's second law. We're going to be doing this for different sort of unit vector orientations, so we can do it in Cartesian coordinates like we did here, where we're talking about x, y, or z directions. But equally fair game would be tangential and normal directions, and look at forces acting in those directions, or also polar coordinates and even cylindrical coordinates. What comes in handy is for those polar and cylindrical coordinates, and even for tangential and normal, we have particular ways that we have expressed the accelerations, and so we can use those results from chapter 12 when we look at the forces for those different coordinate systems.